Do you think it's recording, Ben?
Yeah.
Hello. Hello. You want to know who else is in the room, don't you? So here we go. Let's just do this. Everybody say hi to the DECA folks. DECA, not here. They're on a really important educational field trip. I'm not going to say anything negative because this is being recorded. I could lose my job. No, I don't know where that line is. Yeah, there it is. Okay. All right. 55. Are we on? We're going over homework problems, starting with 55. Alex said, and
55.
did we do 55?
Yes.
So we're starting with which one? 59. We're starting with 59. Who's going to read though? Maylin's not here. Volunteer. Read 59, or do I need to pick somebody? All right, Caitlin, you have to read 59.
Okay.
I'm gonna mix it up though. Next time I'm gonna call on Grayson. Then I'm gonna call on Franklin. I'm gonna call on Alex. I haven't really decided that. I'll forget those names I just said. We're on 59. Go ahead, Caitlin.
A 67-kilogram person jumps from rest off a 3-meter high tower straight down into the water. Neglect air resistance.
Okay, hold a second. This person has a mass of 67. There's water down here?
Mm-hmm.
Okay. And this is 3 meters to the water, right?
Yes.
And now what happens after that?
She comes to rest at 1.10 meters under the surface of the water.
1 point what?
1.1.
Okay. Down here she stops moving through the water. Okay.
Determine the magnitude of the average force that the water exerts on the diver. This force is non-conservative.
All right. So up here she's at rest. Up here she has U, but she doesn't have any K. She's not moving yet. And then she falls to the water, and the water then slows her down until she gets to here and stops. So down here at the very bottom, here's the thing about potential energy. You can decide where H is. Yeah, that's what you need to do. Decide where is H. Where H equals 0. You decide where is the bottom. Some people would say the bottom's here and her potential energy was mgh, where H was just 3. But if you do that, then she's got negative potential energy down here. And you can do that, that's all right. What I'm going to do is say this point where she actually stopped, that's where H is 0. And you can do it either way. But I'm going to say H is 0 here. So her potential energy when she stopped down here was 0. That's where finally she got to the bottom. That means her potential energy up here, though, was her mass, 67, times G, 9.8, times 4.1. You see where I got the 4.1? 3 meters to the water and then 1.1 meters further. That's how high she is above H equals 0. So that's her potential energy at the top, and all of that potential energy is gone when she gets to the bottom. Some of it was turning into kinetic until she hit the water, but then the water slowed her down, and when she stops down here, she doesn't have any kinetic either, does she? So her kinetic energy initially was 0, and down here her kinetic energy is still 0, so kinetic doesn't even play a part in this story. Well, why did she slow down? Why did she slow down?
Water.
The water did some what on her? Work. So it was work done by the water, which was, and work is force times the distance, right? It's going to be, you can think of it as negative work because the water is pushing up on her, which slows her down. And she's still moving down, but the water is pushing up. But the question is, how much did the water push up? What's the force? And so conservation of energy, you can always start with K plus U equals K plus U plus work done by something outside the system. Well, that's the water. That's the work done by the water in this equation. The K's, we already said, you could just mark out, they don't really play a part in this. And so if you solve this for work done by the water, that would be equal to U2 minus U1. Well, U2 is 0. We just said that right here. That's at the this is position 2 when she goes as far down as she's going. And here's position 1. So U2 is 0. So what you have is 0 minus this, whatever that thing multiplies out to be. But it's going to be negative, and you would expect it to be negative because she's moving down, but the water's pushing up. See, that's what negative work is. So that probably should be the right answer. Oh, I'm sorry. Wait, the question wasn't work. I didn't answer the question. The question was force. If you solve that, you get the work done by the water, but that wasn't the question. The question was what is the force? And so instead of W, let's put FD. And the D, what was the D? What was the D?
1.1.
It's 1.1. It's the distance that the force was being applied. Well, the force was being applied just while she's moving through the water. So there you go. If you put 1.1 there and solve that for F, you'll get the right thing. It's always good, in fact, especially me, I do this all the time. I will work out a problem and think I've answered it. And so I've learned what I need to do is go back and reread the question before I move on. Sometimes I got an answer when I go back and read the question. I didn't really answer that question, which is what I just did a moment ago. I said, I've got the work done by the water, and I thought I was through, but that wasn't the question. The question was, what's the force of the water? Okay, yes.
Isn't that supposed to be 67, not 6.7?
67. Oh, you mean this right here? Yes. I got 67 over there, but I put a point over here. Yeah. I even put it right here, but I put a point there. 67 times 9.8 times 4.1, all that divided by 1.1. That should be the right answer. And according to my paper, that comes out, it rounds off to 2,450 newtons. Okay. All right, that's 59. What's the next one we need to work? Did you do 65, 63? 63 is not that important. You had to change a joule to or a kilowatt hour to joules. Did you do that? That's just a conversion problem. The important thing there is that you realize a kilowatt hour is a unit for energy. If you just look at the equation for energy, let's do this real fast. It's work divided by time, or we said work could be any kind of energy divided by time. If you cross multiply, you get energy PT. Well, that's a kilowatt hour. See, a unit for power is the watt, a kilowatt's 1,000 watts. So that's the unit for power, and the hour is a unit for time. So the kilowatt hour is not an SI unit, but it is a unit for energy. And the question was, 1 kilowatt hour would be equal to how many joules, and you're not ever going to really have to convert that on a test, so I'm not going to go over it. But I do want you to know this equation. Power is energy divided by time. So if you multiply power times time, you've got energy. And that's what that is. The kilowatt hour is a unit used when they give you a bill for your electricity. Yeah, you get an electric bill from NES, and what they do is they tell you how many kilowatt hours of energy you have used up in your house, and they then bill you so much per kilowatt hour. So that's just a unit they use. They don't use joules. Okay, so that was 63. Now you tell me which others besides that we need to do in this next set of homework. Which ones do we need to do? Anybody? Call out the number. What was it?
75.
75. I've got a 75 going. What else? Any of them you might have missed? and you're not sure why. Or you just don't know how to work it, besides 75.
Horsepower.
So what, which one?
67B.
67?
B.
B, all right. 67B. Is that the one about the horsepower?
Yes.
You don't really have to know horsepower either. However, there is a conversion number in the front cover of your book, if you ever want to know it, for horsepower and watts. Just do that. So you do need to come up with 10,000 watts. This is number 67. The first answer is 10,000 watts. But then when you convert that to horsepower, you just look up the conversion factor in the front cover of the book. You won't have to do that on the test though. So I'm not too worried about part B. You do need to answer part A. Anybody have a question about part A on 67? Want to do that?
Sure.
Yes? Okay. Well, we'll still do 67. All right, so I'm doing 67 and 75. What else? Yes.
Could you do 73 part C?
73, we can do that. Okay, let's look at 67. Then we'll still go, oh, yeah, 67. And then I'll still ask you if you have any more besides these. Who's gonna read 67? Is it Grayson? Go ahead, Grayson.
The cheetah is one of the fastest accelerating animals because it can go from rest to 27 meters per second in 4 seconds. If its mass is 110 kilograms, determine the average power developed by the cheetah during the acceleration phase of its motion.
Give me those numbers again. It can go from 0 to what?
From rest to 27 meters per second in 4 seconds.
In 4 seconds, okay. And what's the question again?
Determine the average power developed by the cheetah during the acceleration phase of its motion.
Okay.
Express your answers in watts and horsepower.
All right, well, power is the work divided by time. So, and the time is 4 seconds. So how much work did the cheetah do in accelerating from 0 to 27? Well, the work would be equal to its change in kinetic energy. That's the work energy theorem. Or, let me remind you, you can always go back to this. If you read a problem and you feel like it could probably be done with energy methods, but you're not sure how, write this down. Work by something other than gravity. Write it down and you say, well, the cheetah never did go up, so the potential energy is not really part of this story. It didn't go up or down, it didn't change height. So both U's are marked out. So the work done by the cheetah has to be equal to K2 minus K1. See that? And that, so you started with the conservation of energy, but when you marked out the U's, you got the work energy theorem. It's the same thing. It all this and this all come from the same thing, conservation of energy. And so this work will give you the number to put here and divide by 4. And K1 was 0 because the cheetah started out at rest. It wasn't moving, so that's 0. So K2 is simply 1/2 mv squared, where the v is 27. And that's equal to the work done by the cheetah, and then the power would be that work divided by the 4 seconds. So that's the time it took the cheetah to do that. So that's that answer, I think. That's what comes out to be 10,000, or at least it rounds off to 10,000 watts. Joules per second, or watts. That's the first part of 67. Now, if you want to know how to do the horsepower thing, the number was this is in the front cover of your book. 1 horsepower is equal to 745.7 watts. That's the conversion factor, so you just take this times that, and or you would actually divide it. Let's see, horsepower. Yeah, you've got watts. 10,000 watts would be how many horsepower? So you would divide by 10,000 divided by this would be the answer, which is 13 or 12 or something. Am I
Can I
all?
see that?
Horsepower. What'd you
Can I
say?
see that?
Oh yeah, past the line. I'm sorry. Sorry, Decca. Should have been here. It's all right. Not mad. All right, but you don't have to know the horsepower thing. That won't be on your test. This, you need to be able to do this. Find the work done by the cheetah and divide it by the time, and you've got the power. The power of the cheetah. And, oh, did you all see my cheetah? There it is. Yeah, I thought they'd want to see the cheetah. All right. What's the next one, 73? Let's look at 73. Who's going to read 73? Is it Franklin? Read 73, Franklin.
The graph shows the net external force component F cos of
Which one? Is
theta
it?
along the displacement as a function of the magnitude S of the displacement. The graph applies to a 65 kilogram ice skater. How much work does the net force component do on the skater from A, 0 to 3 meters, and B, 3 meters to 6 meters? And then C, if the initial speed of the skater is 1.5 meters per second when S equals 0 meters, what is the speed when S equals 6 meters?
Okay, what was the first question? I
Um,
think I've got the graph sort of.
how much work does the net force component do on the skater from 0 to 3 meters?
Okay, the work done during the first 3 meters. And the force was 31 newtons. This is distance on the x-axis, these are meters. So, if work is force times distance, it's pretty easy to see that would be 31 times 3. Now, I think the point of showing you this graph though was, it would be the what? Graphically, instead of saying it's force times distance, you could look at the graph and say, oh, that's the what of the graph? Area. That's the area under the curve. Or the curve is just this. Well, it'd be the area of that rectangle, which would be length times width, so that is 31 times 3. So it looks like that's something like 93 joules. So if you have a force distance graph, since force times distance would give you the area, you know, even if the graph did some funny thing, still the area under the curve is the work done. Okay. So for 3 meters, it was 93. And then what's the next question? Is it 6 meters?
From 3 to 6 meters.
From 3 to 6, the force was 0, wasn't it? Also think, well, what's the area under the curve from 3 to 6? It's 0. So the work done there is 0. Okay. There's no area under the curve. Also, if you just think force times distance, the force is 0. From here to here it is. So that work is 0. And then there was another question, is that right?
Yes.
All right, what's part C?
If the initial speed of the skater is 1.5 meters per second when S equals 0 meters, what is the speed when S equals 6 meters?
Okay, so when it moves a distance of 6, by the time the skater has moved 6 meters, what's the speed? The work done was 93 joules. The total work, because none was done here. And the work done has to be equal to the change in kinetic energy. For the same reason we said up here, the U's are going away, the skater never did go up and down, there's no height. So take out the U's and you get this. Work is K2 minus K1, and the K, oh, they gave you initial speed, so there is a K1, that would be 1/2 the mass. Do we know the mass of the skater?
Yes, it's 65.
Oh, okay, it is what?
65 kilograms.
65. All right, so 1/2 the mass times the 1.5 squared, that's the initial kinetic energy. And then the second kinetic energy is 1/2 the mass, 65, times v squared. And the work done was 93 joules. And so I think wait, there's something wrong here. What is it? The work done is 93 joules. The final kinetic energy is 1/2 mv squared. We don't know v. The initial kinetic energy is 1/2 m1.5 squared. So maybe that is right. Did you all do this and get 2.3? Anybody get 2.3 meters per second for the answer? You did, Franklin?
I did.
Yeah, I think that's still right.
Yeah, that's right.
Okay,
What was the answer?
2.3 when you solve it for V. 2.3 meters per second. Okay, I think that's right. Okay, so you need to get the graph thing that the area under the curve, if it's a force distance graph, the area under the curve is meaningful, not the slope. It's the area under the curve that is work. And then you need, of course, this is just conservation of energy then, to figure out that the work is equal to the change in kinetic energy. All right, that was 73. Is everybody okay with that now? Then let's look at 75. And I think the reader should be, who did I say before? Was it Alex? I don't know if it was or not, but Alex, I want you to read 75. Do you have your book open? Yeah, go ahead.
A net external force is applied to a 6 kilogram object that is initially at rest.
Is there a graph with this one?
Yes.
Oh my goodness, I'll never get that. It's force and distance, and it goes up to what, 10?
5, 10,
5 and then 10, that's 10 and 20. Okay, maybe. All right, here's my force distance graph, and it goes from here up to here, where that's at 10, and it goes across there,
This
and this was at what,
10.
5?
10,
This was 10?
yes.
This was 10 and that was 20, yeah. Is that kind of what it is? All right, go ahead and read.
The net force component along the displacement of the object varies with the magnitude of the displacement as shown in the drawing. What is the speed of the object at s equals 20 meters?
The speed here, all right, you're going to have to use conservation of energy again. From the graph, you can get the work done. The work is the area under the curve again. So in this case, I would find the area of this triangle and find the area of this rectangle and add them together. This is 1/2 base times height, of course, that's length times width. I have that the work, this is the area under the curve, it's equal to the work, and I have that adds up to 150 joules. You just find the area of this and the area of this and add them together. It's 50 plus 100. Okay. Then, and maybe, was that question A? Maybe it
No,
was.
You're looking for the speed of the object.
No, okay, we want the speed of the object. Speed of the object would be this again, where work is equal to K2 minus K1. Again, that comes from this if you take out the U's. The work we now know is 150 joules, and the K2 is 1/2 mv squared, and the V is what we don't know. And K1 though was 0, right? It wasn't moving at all. All right. so minus K1, but K1 was 0, not moving initially. So I think if you just solve that for V, you'll get it. Yeah, the mass was given as 6. So you can solve that for V. Does that make sense, everybody? Does that make sense, DECA students? It does? What, Robbie? It's 6, the mass is 6, Robbie. I was given in the problem. All right, any more questions about about this assignment that went up to 75? Any of those problems? Any more? Are we okay with that? Ready to go over focus questions? All right. Focus questions. In your book. What time does this period end, Caitlin?
11:07.
We still have 12 minutes or so. Hey, DECA, I'm going to take this video. Here you go. I'm going to take this video and upload it to YouTube. Maybe. Claire Eakes told me I could do that. Do y'all know Claire?
Yeah.
She has a YouTube channel, account, whatever you call it, that she records the Physics 2 lectures all the time, and in here, and she leaves them there. So she told me I could take this one and put it there. It's called Mr. Claxton's Physics 2. No, Mr. Claxton's AP Physics 2. I think. I'll check that out. Anyway, DECA, go there and you'll see this. You don't know I just said that unless you already got there. All right, I'm looking for the focus questions. Here we are. We're going to go over them now. Number 1. The same force F pushes in 3 different ways on a box moving with velocity V. As the drawing shows, rank the work done by the force in ascending order, smallest first. So tell me, Dan, what did you pick for number 1? E is an egg. Anybody else put E? You are correct if you're raising your hand now. That is correct. How much work is done in C? 0. So you need to know that, of course. And then A is less than B because it's at an angle. All right, look at number 2. Consider the force F shown in the drawing. This force acts on an object that can move along the positive or negative x-axis or along the positive or negative y-axis. The work done by this force is positive when the displacement of the object is along the what axis? How'd you answer that, Zoe?
B.
B, so the negative x, is that what you said? And, or along the, what in the world? Now I'm confused, I confused myself. The work done by this force is positive when the displacement of the object is along the positive y-axis. Because the force is up, part of the force is up and it's moving up. Or it could be along the negative x-axis. Yes, because part of it's moving left. So yeah, negative x or positive y, it is answer B, you are correct. All of you get B? Took me a while to see what was going on there. Yeah, if the force is in that direction, then it is pushing up and left, both. So as long as the object's moving either up or left, then it's positive work. All right, I'm on number 8. 2 forces, F1, F2, act on a particle. As a result, the speed of the particle increases. Which one of the following is not possible? What did you put, Grayson, is not possible?
I put E.
E is an egg?
Yeah.
Anybody else put E? Oh, there are only 2 people who agree with you, Grayson. You wanna change your answer? Don't answer that. Number 8. E says the work done by F1 is positive and the work done by F2 is negative. That's not possible. That is possible if the work done by F1 is greater than the work done by F2, then the net work will still be positive. So it's not E. It's not E. So if you know it's not E, Han, what do you think it is? Number 8. The speed increases, so what you know is it's positive work. Now, which one did you pick? Han, did you say D? As in dog? Anybody else agree with D? It is D. You are correct. And that's what you need to get from the question. If the speed increases, then the net work from the 2 forces has to be positive. Okay, negative work would slow it down. So the 2 F's have to add up to something positive. So D is impossible. It says the work done by each force is negative. If they're both negative, then the work is negative, and that's impossible. It would not speed up. So that's the one that's impossible. D. Number 9, force F1 acts on a particle and does work W1. Force F2 acts simultaneously on the particle and does work W2. The speed of the particle does not change. Which one of the following must be true? This is a good one. Mackenzie, what do you think? Boy? Anybody else put boy? You are correct. B says W1 is equal to negative W2. They're canceling each other out. So that's why the speed didn't change. Very good. Number 11. A person is riding on a Ferris wheel. Do you know, Han, what a Ferris wheel is?
Oh, it's in your kind of
You sit in it and it goes around like this. Yeah, a big vertical circle. Did you know that, Dan, the Ferris wheel? Yeah. Have you ever ridden on a Ferris wheel? You have? Have you, Dan? Have you, Alex? Have you, Caitlin? Ferris wheels are fun. Where are we? When the wheel makes one complete turn, the net work done on the person by the gravitational force. Kevin, what is it? What did you put for 11?
I think it is B.
B as in boy?
Yes.
Anybody else put boy? A couple of you did. But it's not boy. The work done by gravity is negative. Now notice the wheel turns one complete revolution. It goes from here all the way back down to the same spot, or whatever. So if I tell you, Alex, that it's not B, what do you think it is?
C.
Did you say C as in cat?
Yes.
Anybody else put cat? Cat is correct. It's 0. Why is it 0? Alex, why is it 0?
Came back to the same spot.
It came back to where same place you started from. Now, also, here, think about it starting at the bottom and ending at the bottom. One thing you know is displacement was 0. It started and stopped at the same place. Work done is force times displacement. But also, here's how you think about it. As it's moving this way, gravity's doing work on it. What kind of work?
Negative.
It's negative because gravity's pushing down, but the person's moving up. So gravity's doing negative work. Then from here down, though, gravity's doing what kind of work?
Positive.
Positive. And so if you actually added that and you added that, it would add up to 0. Because the distance is the same, but this is negative and that's positive. So you can think of it that way as well. You still get 0. Okay. We have time for at least one more, 13. In which one of the following circumstances could mechanical energy not possibly be conserved even if friction and air resistance are absent? What do you think about that, Ben?
D.
Did you say D is in dog? Anybody else put dog? 1, 2, 3, 4. 4 of you are correct. It is dog. Dog says a car moves up a hill at a constant velocity. Why is that not conservation of mechanical energy? It's just a word kind of
Because
thing.
it has said, since it's going uphill, it has to work against gravity.
Yes, it is working against gravity. If it's not slowing down, see, gravity would be slowing down, but it's not slowing down, then what's going on?
It's working out.
It's getting some work done on it by the engine. It's applying a force, and it's moving a distance as it moves up the hill at a constant speed. So if it's getting outside work, which is what the engine does, then mechanical energy, K plus U does not just equal K plus U. For mechanical energy to be conserved, K plus U equals K plus U. There's no outside work involved. That's what the question means. Okay. All right. We can do another one still, I think. 14. We're not out of time yet. A ball is fixed to the end of a string, which is attached to the ceiling at point P. As the drawing shows, the ball is projected downward at A with a launch speed VO, traveling in a circular path. The ball comes to a halt at point B. What enables the ball to reach point B, which is above point A? Ignore friction. Caitlin?
B.
B is in boy. Anybody else put boy? A couple of you put boy. Boy says the ball's initial gravitational potential energy. If that was all it had, though, it would only rise to the same level. So if it started here and all it has is U, then it would move over here where it had the same U. If it stopped there, it wouldn't go higher. So that's what's wrong with boy. It has to be something else. What do you think, Franklin?
C.
Anybody else put C? Cat? C is right. The ball's initial kinetic energy. That means if it started here, you had to give it a push, or maybe it really started up here, and you let go of it. So when it reached this point, that is position 1, but it already had some K, and that's what the answer says. It has initial kinetic energy here, so K plus U are enough to get it farther than the position here, and it finally stops up here where it's higher, because up here it has only U. Up here it stopped, so it has only U, and that's equal to K plus U over there. That U would only equal this U if it had no K. That U would get it to here. If you want it to go higher, you just got to start with more than just U. That's the idea. Okay. Is that the last one?
25.
25. We can do it real fast. We have 45 seconds. The power needed to accelerate a projectile from rest to its launch speed is V is 43 and time T is 43 watts. How much power is needed to accelerate the projectile? You had to actually calculate this. What did you get? Han, your hand was up. What did you get? Is it 300 something? Anybody get 300 something? It is 300 something. Grayson, 300 what?
44.
344 watts. We might need to work that tomorrow. Your homework is the practice test, so pick one up. They're right there next to Caitlin. Caitlin's going to make sure each of you gets one. I'll see you tomorrow. If you're in DECA, you better get a practice test.